Good morning. My name is Charles Forsberg from the Massachusetts Institute of Technology. My co-author is Bruce Dale from Michigan State University. Today we would like to discuss replacing liquid fossil fuels with liquid biofuels from large-scale nuclear biorefineries. We would like to cover 4 subjects today. First, the low-carbon liquid fuels challenge and its characteristics. Second, large-scale liquid biofuel system to minimize cost and maximize energy content. Third, low-carbon nuclear heat and hydrogen inputs into biofuels. And last, some concluding remarks. Let's take a look first at the low-carbon liquid fuels challenge. Why we want low-carbon liquid fuels. We start with the observation that most energy is used as heat. In the United States, electricity is only 17.5% of consumer energy demand. If you wish to electrify the economy, you would have to increase electric production by a factor of 5. The figure shows the current energy distribution markets in the US. On the left, we have energy sources: solar, nuclear heat, wind, geothermal, fossil heat, natural gas, coal, biofuel, biomass, and fossil heat. On the right, we have the consumers: the residential sector, the commercial sector, the industrial sector, and the largest sector, the transport sector. In the middle, we have what happens to our energy conversion systems. We have the electric sector, where the electricity output is in gold, and then we have the heat input into the various sectors. One immediately observes is that most of the customers want primarily heat, not electricity. And so the question is how to provide that heat. The second observation we make is that low carbon biofuels can provide a replacement for the storage function of fossil fuels. Now, the total US daily energy demand is about 70,000 gigawatt hours. If you want a point of comparison, a large nuclear plant produces 3 gigawatts of heat, or 72 gigawatt hours of heat per day. US energy storage today is measured in millions of gigawatt hours. Impressive number. Fossil fuels, we typically have a 1 to 3 month supply of fossil fuels, primarily dependent upon the season of the year. Nuclear has about a 9-month inventory of nuclear fuel in a typical reactor core. Wind and solar PV have 0 storage. Now, the problem this raises is as follows. A low carbon world has almost no energy storage, no resilience to weather or other external events. And thus, there's a strong incentive to use liquid biofuels that can replace fossil fuel energy storage on a very large scale. The third observation we'd like to make is about electric vehicles. In particular, we want to take a look at a California study which shows that the electrical profile of all electric vehicles results in big trouble for the grid and very large incentive for biofuels. At the figure on the right shows the expected charging times for electric cars in California over a period of 1 day. The peak demand for electricity for recharging electric vehicles is about 8 p.m. in the evening for a variety of reasons. Unfortunately, this peaking demand in the middle of the evening is a nightmare scenario for the grid. Peak electricity demand from cars, at the same time peak electricity demand for other applications. In contrast, plug-in hybrid cars, that is cars with batteries plus internal combustion engines, help the grid. First, the car is always available. There's stored energy on board in the form of liquid fuels. Second, you can charge the vehicle when electricity prices are low and when there's excess electrical capacity on the grid. Helps the grid. Third, it turns out that hybrid vehicles have smaller electric batteries and hence are lower priced vehicles. The grid and cost challenges of an all-electric system create large incentives for storable, low-carbon biofuels. This raises the next question. What is the availability of biofuels? What is the market potential? This particular view graph shows the results of 5 studies on the availability of biomass on a global scale. And what these studies show is, on the average, biomass energy could meet a fifth or a quarter of total global energy needs. Now, what we're talking about here is the biomass energy, for example, if you light a match under it. However, we can convert biomass to biofuels, adding external heat and hydrogen that can increase the energy content of the biofuel. And so the biofuel energy content can be much greater than the biomass feedstock energy content. In other words, we could provide more than a quarter of the total energy demands to the customer, the final customer who needs the heat source. With that, let us take a look at large-scale biofuel systems to minimize cost and maximize energy content. First, low-cost biofuels require large-scale cellulosic biorefineries. There are massive economics of scale associated with chemical plants, and thus a biorefinery should be in size equivalent to a 250,000 barrel per day oil refinery. We want to use the same strategy as the oil refineries, where large refineries are more efficient and have much lower costs. Second, which is not so obvious, a large refinery can produce more high-quality product per ton of feedstock by upgrading secondary streams into high-quality fuels. Any process will produce secondary streams. If you have a small biorefinery, a small regular refinery, these secondary streams are not worth processing. They are burnt as fuel, as low-quality fuel. If you have a large facility, you can build custom facilities economically to upgrade these secondary streams into high-quality fuels. A tremendous gain in terms of economics. Last, a large-scale biorefinery enables large-scale low-carbon footprint nuclear heat and hydrogen inputs into the biorefinery. Now, to make a large-scale biorefinery possible, we need high-density biomass intermediate products. The problem is this: current cellulosic biomass forms have major challenges when we talk about bales, chipwood, and so forth. Low density, expensive to store, they degrade in storage. And they're expensive to transport, and economically you can't transport them more than 20 to 50 miles. As a consequence, the storage and transport limits results in small, inefficient biofuels plants with lower capacity factors and higher cost biofuels. So what we need to do is develop densification technologies to enable economically shippable biomass to large biorefineries. As we show in the green squares on the right, we start with cellulosic biomass. We need a densification to produce a dense, transportable, storable form locally that then can enable and be shipped to large-scale biorefineries to produce liquid fuels. Now, the third observation we make is that external energy sources can greatly increase the liquid fuel yields per ton of biomass. We show here the traditional biomass flow sheet. We have the biomass collected in the field, sent to a fuel factory, produces a liquid fuel, for example, to a car. We burn the biomass, we produce carbon dioxide that goes back and is collected again and recycled again by biomass back to the biorefinery. However, that's not the whole story. It turns out fuel factories, biofuel refineries in particular, have large inputs. Let me use a traditional example. If we're making ethanol from corn or sugarcane, we have to feed the yeast to produce the ethanol. In effect, there's a large energy consumption by the biofuel factory. So if we have external sources of heat and other energy sources, we can eliminate the use of biomass as an energy source and increase the yields of final fuels per ton of biomass. There's a second factor. Adding hydrogen can greatly increase the liquid biofuels yield per ton of biomass. In the following table, we show on the left various processes to convert biomass into biofuels. I'm not going to go into the details of it. In the middle column, we show the kilograms of octane fuel per kilogram of cellulose for these different processes. And in the far right column, we show the energy input into these processes in the form of hydrogen. Now, the simple story here is quite straightforward. As we add more hydrogen to our biorefinery, the yield of liquid biomass fuels in terms of energy content goes up per kilogram of cellulosic feedstock. And this enables us to almost double the liquid fuels yield per ton of biomass and produce a high quality fuel product by hydrogen addition. With that, let's turn to the third subject: low carbon nuclear heat and hydrogen input into biofuels. In short, the input that makes possible production of high quality, high yields of high quality hydrocarbon fuels from biomass. Now, in a low carbon world, nuclear plants produce cheap heat. What we show here is a figure of different technologies to produce electricity. In the middle column is the levelized cost of electricity. In the right column is the levelized cost of heat. Now, if you have a typical solar collector or a wind system, they produce electricity. If you need higher temperature heat, converting the electricity into heat results in 1 kilowatt hour of electricity producing 1 kilowatt hour of heat. However, nuclear plants are different. Nuclear plants produce heat, and they produce several units of heat per unit of electricity. So if you have a nuclear plant that produces relatively expensive electricity, it turns out it produces very, very cheap heat. The cost of heat from a nuclear plant is about a third of the cost of electricity. There's a second factor that's equally important. If you produce electricity, you have to deliver it to the customer with an electrical grid, transmission lines, transformers, and other equipment. That transmission system, that delivery system, approximately doubles the cost of electricity. And what it implies is that if you use an electric source to produce heat, it's really, really expensive. That's the incentive for nuclear heat. The other consideration is the production of heat and hydrogen for the biorefinery. Here we show a figure of the biorefinery system and the reactor and hydrogen production systems. Heat is produced by the reactor in the red square and sent to the large-scale biorefinery in the downward direction. Hydrogen production can be done by several methods. The most efficient method is a process called high-temperature electrolysis. That's steam electrolysis of water. It's the most efficient process, and equally important, much of the energy input is in the form of steam, so it produces the lowest cost hydrogen. And this is shown in the gold box. So we have a system here that produces heat and hydrogen as the main energy inputs to the biorefinery to avoid using biomass as our energy source in our biorefinery. Well, what are the high priority challenges? There are three. The first is the need to develop and deploy methods to convert cellulosic biomass into high density, storable, cheap to transport intermediate biomass product to enable large scale biorefineries. We need technology demonstration and scale. Pilot plants exist. We know how to do this, but we need to scale them up. Associated with that is what we call the chicken and egg development challenge. How do you start up the system? You have to have a market for densified products before people will build the densification facilities near the agricultural or forest waste. Second requirement is large-scale biorefinery process development. This may be a lesser problem. The reason is quite simple. If a good economic case exists, the major oil companies will quickly develop the technology. This is a close relative to the technologies used in refineries. They understand this business. Last, the integration of low-carbon nuclear heat and hydrogen for low-carbon liquid biofuels production. This leads us to our conclusions. First, the need for low carbon liquid fuels. Second, the observation that biomass feedstocks are sufficient if massive inputs of low carbon heat and hydrogen at the biorefineries. We do not want to be in the business of burning a biomass to run a biorefinery. That leads to the following path forward: large-scale biorefineries, densification of biomass where produced to enable economic shipment to large-scale biorefineries, and last, low-carbon nuclear heat and hydrogen input to the biorefineries. That completes our discussion today. We'll have a discussion at the conference. If you're interested in additional details, feel free to contact either of the authors. Thank you very much and have a good day.